everyone!
I'm Angeline and I'm here with my friend
Whitney. We're from Harapan Bangsa Christian High School, Balikpapan, and in this video, we're excited to present the results of our research in the Indonesian Science Project Olympiad 2025. We have been working on developing a sustainable and also biodegradable fabric alternative, and throughout this presentation, we will take you through our findings, methods, and also the results of our research. So, let's get started!
Every year, tons of fabric waste pile up, polluting landfills and oceans. The fashion industry is the major cause, with synthetic fabrics taking centuries to break down. Cotton is widely used, but needs too much water and chemicals, making it less sustainable.
What if we could create a fabric that is both sustainable and also biodegradable?
Basically, textile waste is a growing environmental problem, with synthetic fabrics like polyester taking hundreds of years to break down. These non-biodegradable materials pile up in oceans and also landfills, polluting the planet and harming the ecosystem. Even cotton, though natural, has its own challenges because it requires a lot of water, chemicals, and farmlands, which can damage the environment. As the fashion industry keeps expanding, we need better and more sustainable alternatives.
Brown algae could be the solution. This marine plant produces alginate, which is a strong biodegradable fiber that can be turned into eco-friendly fabric. Unlike cotton, algae don't need fresh water, pesticides, or large areas of land to grow. They also absorb carbon dioxide, helping to fight climate change. In Balikpapan, where brown algae are abundant, they could be a game changer for sustainable textiles. By using algae-based biofabric, we can also reduce textile waste and create a greener future for the fashion industry.
In this case, our research question is about what is the potential of algae as a basic material for biofabric to replace synthetic textile materials that are not environmentally friendly.
This research aims to develop algae-based biofabric as well as evaluate the physical and mechanical properties of biofabric as an environmentally friendly textile material that can replace cotton and other synthetic materials. First, prepare the sodium alginate, then add 200 milliliters of water into the beaker and then mix them.
Third, place the mixture in the refrigerator for a few hours to remove air bubbles and improve stability.
Next up, in a small glass, mix 10 grams of calcium lactate with 100 milliliters of water. Stir until dissolved, then transfer to a spray bottle. Then, take the sodium alginate mixture out of the refrigerator and remove any foam on the surface with a spoon.
And we also need to add glycerin to the mixture based on the formula. You can also add food coloring if needed.
The seventh step is to place a piece of canvas inside of a wooden mold and stretch it tightly to make it firm.
Then for the eighth step, we should spray the calcium lactate solution onto the canvas until wet. Now we also need to pour the alginate mixture into the mold and spread it evenly with a spoon. Spray the calcium lactate solution evenly, wait for 10 seconds, then absorb the excess liquid with a tissue for a clean and neat result.
Lastly, let the mixture dry in the mold, then carefully remove the biofabric.
For the biofabric assessment, in this case we will use 6 assessments, which includes first, degradability. For the second one is tensile strength. For the third one is SU. For the fourth one is organoleptic. For the fifth one is about torsion pass. And for the sixth one, or the last, is flexibility.
This research produced 8 biofabric samples with 23.5 centimeters in diameter molded and later cut for testing. High alginate content led to stiffness and cracking, while high glycerin content increased flexibility but reduced durability. F3 had the strongest seam, while F8 was the most flexible, and the following analysis covers 6 key assessments.
Here we present our data for the organoleptic description, which includes aroma, texture, and thickness.
And here are the mechanical properties. The first table shows the mechanical properties of alginate concentration variant groups. This proves that higher alginate content increased tensile strength but reduced elasticity. Formulation 4 had the best properties. And for the second table, it shows the mechanical properties of glycerin concentration variant groups. It shows that more glycerin improved flexibility but weakened the fabric at high levels. Formulation 8 had the best balance. Next up is the sewing results. The sewing test confirmed that algae-based biofabric is sewable with considerations. High alginate fabrics may crack, while high glycerin fabrics tear easily. And from here we can see that F3 had the strongest seam and F8 was the most flexible.
So basically, the algae-based fabric degraded in 7 days. In 24 hours, the color washed out and the texture softened. By 72 hours, most samples shrank, with F4 and F8 breaking down fastest. All samples dissolved by 168 hours, highlighting its eco-friendly biodegradability over synthetics.
From here, we can conclude that algae biofabric is a promising innovation in the textile industry as an environmentally friendly alternative raw material. Further research suggestions includes the optimization of biofabric formula with variations in materials and degradation tests, as well as the analysis of product efficiency with economic feasibility to increase its competitiveness.
We are also planning to create shopping bags and clothes from these biofabrics because it is an eco-friendly, sustainable material that can be adjusted for flexibility and strength. At the end of this video, I would like to close it with one quote, which is, "Sustainable fashion is not a trend, but it is about our future." I think that's all from our video, and we hope that our research can be useful. That's all from us.